We're now going to have a look at our final class of types of functions that we can find derivatives of, which are parametric equations and parametric curves. In order to describe a particular curve, we often have to use a set of parametric equations where x and y are related through a parameter value, and this allows us to draw very complicated curves indeed. We're going to have a look at these and also how to find derivatives of these. So say we have some curve, which is obviously very difficult to write down as a function, but with a parameter t which increases along it, and so on. Given a value of t, this specifies through the functions f and g x and y values, and then increasing t smoothly generates a curve. This is obviously very useful for physics, for example, where the parameter might be time, and the functions x and y could be just locations in space, for example. So we have seen, for example, if we let x equal cosine of t and y equal sine of t, that draws out the unit circle. We can have a look at some different functions. For example, if we look at x equals cos t and y equals sin t, so analogously to a circle, that draws out a hyperbola, which is for one of the reasons why cos and sin are known as hyperbolic trig functions. We can draw more complicated things, where we can draw a spiral, for example, if we increase the parameter t in t times cos t, and y is root t times sine t, that traces out a spiral. And then one can trace out some even wilder shapes. So for example, this famous butterfly curve is given by these complicated functions, and other types of very exotic behavior can be drawn. So even though the curve itself might be very complicated, we can still find the derivative dy by dx as follows. Using the chain rule, I can write dy by dx as dy by dt, dt by dx. And I can write dt by dx as 1 over dx by dt. So dy by dx is a derivative with y with respect to the parameter t divided by the derivative of x with respect to the parameter t. Or you can think of this as g prime of t over f prime of t, where prime equals d by dt. So if we just recall the example of a circle, so given the derivative of x with respect to t and y with respect to t, this implies dy by dx is minus cos over sine, which is cot, which is just minus x over y, which is what we found earlier. Let's have a look at some other examples. Let's have a look at a curve called the asteroid, which is x equals cos cubed t and y equals sine cubed t. This traces out this star-shaped pattern as t increases from 0 to 2 pi. We can find the derivative along this curve as just dy by dt, which is 3 sine squared t cos t, divided by derivative of x with respect to t, which is 3 cos squared t times minus sine t. And that simplifies to minus tan t. Now, does this make sense for the derivative? Well, let's quickly sketch out the curve. So that's just a rough sketch of the curve. Let's then add on the parameter values at the critical points of the function. So we start at t equals 0 here. The parameter t increases till we get to this spike at the top. Parameter keeps increasing to t equals pi when we get to the spike on the left. Then we go around the curve some more to 3 pi by 2. And then finally we get back to the start as t approaches 2 pi. If dy by dx is minus tan t, then the gradient is equal to 0 at t equals 0 and pi, and that correlates with the graph, so the gradient, or the slope of the curve, so that's here and here, the slope tends to 0, and as we go through t equals pi by 2, the gradient goes up like this and then down again. So the gradient goes up to infinity and then becomes minus infinity as it goes down again. And the reverse happens at t equals 3 pi by 2. So this is an example of a feature called a cusp. A cusp is a sharp point on a curve where the derivative does not exist. So it's not differentiable, and in fact if you zoom into this point, it never smooths out. If you remember that we came into differentiation with the idea that we could keep zooming infinitely far into a curve and it eventually becomes equivalent to a straight line, This is an example of a point where that never happens. You can zoom in as far as you like, and it just tends to an infinitely sharp point. Let's have a look at a curve called a cycloid. A cycloid is the curve that is generated when you roll a wheel along the floor and follow out a path which is a fixed point on the wheel that's traced through space. If you just try and imagine what that curve looks like, let's have a look at it just now. As we roll a wheel along the floor and follow a point in space, this traces out a curve. This curve is called a cycloid, and it has some rather simple parametric equations which go with it. Let's just derive these now. Let's start the wheel rolling with the point on the floor that we're going to trace from. If we take it a short while after it starts rolling, let's see if we can parameterize this system. The radius from the center to the point on the wheel that we're going to follow. Let's now drop down the vertical line to the floor, and let's start drawing in some features that we can see about this curve. Let's call this angle in here theta, and let's also draw in the horizontal line from the point on the wheel that we're following to the vertical. Now, if the radius of the wheel is r, then I can start drawing in some geometric features of this. The horizontal distance is given by r sine theta, and the other side of the triangle is r cos theta, which means that the distance from this point to the floor is r minus r cos theta. So those are some useful things associated with the angle theta. How can we now get some parametric equations? Well, let's draw on a set of suitable coordinate axes. The axes that I'm going to use are the x-axis for the ball rolling along the floor, and the y-axis I will choose to coincide with the start of the cycloid curve. As the point P traces out the cycloid, I need to know the coordinates of the point P. So let's label these x and y. How can we find this? Well, we can already read off that y is equal to r minus r cos theta, the distance of the point P above the floor after the wheel is rotated through an angle theta. What else can I write down on this? Well, the distance from the origin to the center of the circle along the x-axis, this is just r theta, and that's just the arc length of the wheel that is rolled along the floor. And therefore, we can read off the parameter x as the distance from the origin to the center of the circle in the x direction minus the distance back to x, which is r sine theta. So x then is r theta minus r sine theta. And so by just drawing out the geometry of the situation, we come up with the parametric equations for the cycloid. As theta advances, every 2 pi, the wheel completes 1 revolution, and then we can keep drawing out further arches of the cycloid as theta increases beyond 2 pi. There's no reason to restrict it to 0 to 2 pi. Let's now find the gradient along this curve. So again, using the chain rule, our parameter is now theta, r is just a constant, dy by d theta divided by dx by d theta, and this is just r sine theta divided by r minus r cos theta. And notice it doesn't depend on the radius of the wheel. So the slope goes to 0 whenever theta is any multiple of pi, so 0, pi, 2 pi, and so on. And when 1 minus cos theta is equal to 0, the derivative becomes infinite again. So this is an indication of another cusp in the graph. So if we just draw a rough sketch of the graph, then if we just label on which values of theta go where, theta equals 0 is our starting point. Theta equals pi is at the top. Theta equals 2 pi is in here. Theta equals 4 pi is in there, and so on. So in these points we can see theta equals 0, theta equals 2 pi, theta equals 4 pi are cusps where the gradient goes from minus infinity to plus infinity, and dy by dx equals 0 at theta equals pi, theta equals 3 pi, and so on. In order to evaluate theta equals 0 and theta equals 2 pi and 4 pi, when sine theta goes to 0, we actually need to work out a bit of a complicated limit. We'll need to do this later in the course when we study what's called L'Hopital's rule.